Guys, let's now continue our discussion on the limit analysis procedures. Okay, so I have given an introduction how limit analysis works with the basis of a mechanism approach. And to continue with that, I'd like to present to you now the approximate procedures, actually general procedures on how to conduct a unit analysis or a class analysis uh, in general. Okay? So the first one is called the mechanism method, just like what we did a while ago. And this method determines the ultimate load for a possible assumed collapse mechanism or a failure mechanism. Okay? So in this particular approach, what we have to bear in mind is that um, the procedure or the method is actually within the bounds of the upper bound theorem, wherein the ultimate load uh, that is computed, so this is the calculated load, is always greater than the expected or the actual load we expect uh, to be carried by the structure. And in this particular slab analysis, this method pertains to the lead line analysis. So this is the lead line analysis for slabs. So we're talking here of slabs. And this is a very unconservative uh, solution because the computed load or the actual, the calculated load using the analysis is always greater, falls at the upper bound of the expected load that the structure can carry. In short, this is now the real load that the structure will be able to carry. Ultimately, so the checking on this is perhaps done by simply noting that the moment or endpoint is always less than the plastic. Okay, so I'll show you the graph on that later. So for the next method, we have the statical graphical load method, which is actually demonstrated by the strip method that we will be discussing later. Okay, so this is the SN strip method, which is a lower bound criteria in terms of limit analysis. Okay, simply because your calculated loading ultimate is always less than the actual load. So this is more conservative than the first one. If this is conservative, this is actually conservative, since the ultimate load determined from the kinematically admissible field is always less than the absolute. So example of a mechanism method in beams, no, is simply done basically using many methods, but I would like to present to you the mechanism method in terms of the virtual what we call energy method. So if you do the virtual or energy method, still remember basic theorem regarding this. You take note that if you load a prop beam, same prop beam, okay, so this is the same beam that we're talking about a while ago. we assume somewhere at the middle, so this is just an assumption, somewhere in the middle that there will be a plastic hinge that will be formed here, and another plastic hinge that will be formed at the fixed point. So this is a real hinge. Okay? So then we can now compute for the ultimate load W that will be uh, created, no? That will be obtained by using the assumption in the system. And from the figure itself, we take note that the rotation upon which this fixed end uh, will uh, exhibit, no? Will be needing an energy or a work virtually to do it. Okay, so this will not repeat if there will no uh, if there will be uh, if there is no energy, internal energy that is happening, or internal virtual work that is happening inside this hinge. Okay, and upon rotating this, we can say that the energy is simply the work or the energies can actually be a force times distance or simply a moment times rotation. Okay, so in this case we have here a theta equivalent to this, and again this rotation here we will be needing another angle which is equivalent to 2 theta delta, because this is also assumed to be theta since this is symmetrically balanced not the midspan element. So this is 2 theta, but in the real hinge you need no energy here virtually. You don't need any internal energy at the real hinge. So what you need now are these two internal work and one external work. So you have an external work. So the external work done in this system is induced by the ultimate load that you are computing here. Okay, and if you want to compute uh, uh, this work done, you have to divide this into two segments. No? So it's simpler if you divide this into segment number one. Okay, rotating at a certain angle like this one. So if this is your work here, so it's WU times L over 2 is your force. Okay, that will be created. So this is W times L over 2. Okay, multiplied by this is force. So this is a force. You need a distance or a deflection somewhere uh, in between. Okay, so if you take a look at the uh, deformation at the centroid, okay, so you have here a delta. So this delta is equivalent to the rotation multiplied by a certain distance from point here, which is L over 4. Okay, so this is delta is equal to theta uh, times L over 4, which is basically uh, at, okay, at the left hand portion. So if you have two segments here, one at the left and one at the right, the total external work done in terms of delta, so this is now your delta is will be simply equal to 2 times theta L over 4, which is simply theta L over 2. Okay, so you can cancel out 4 there and this becomes 2. So this is theta L over 2. And manipulating this one here will yield to an expected result of your ultimate or your plastic load calculated, which is 12 ampere square, slightly greater than the previous one that we have derived using elastic, okay, using elastic procedures. So this elastic procedure, uh, in terms of the limit of the loading is not very far, so the difference is small, no? So the range elastic and the ultimate plastic have a very small, okay, discrepancy. So might as well use the the, uh, the mechanism method uh, based on assumptions of at near, okay, at the near midspan, rather than using an exact elastic uh, approach in the computation uh, of your ultimate load. And if we want to check it here in this graph, what we have done in the previous is that we assume this to be having an empty equivalent at this point. So this is empty. So you will notice that my load, my load for this, this is empty. The energy, the diagram here is smaller than the diagram previously defined on this basis. So my MP here are just the same if we are talking about the same pin, but the ultimate load is slightly bigger if we are using it exactly at L rather at 5 over 8. So this is 5 over 8 L. Okay, so that is the comparison between the two uh, methods, the graphical uh, and the mechanism method. Also, this is pertains to the mechanism method. For the graphical method, we will go straight on the strip method later to enlighten you on the procedures on how to deal with this lower bound principle of theorem. Thank you very much for listening. Have a nice day.